Hey, what's up everybody? Alright, we're going to talk today about expanding binomials. And there's a few different methods for doing that. The goal here is that you're going to use the binomial theorem in particular to expand a binomial that's in the form a plus b to the nth power. Alright, so you can use Pascal's triangle, you've probably learned that before, but we're going to use the binomial theorem in this video in order to be able to expand binomials. And there's a formula that we're going to use to do that. Or at least a form, if not a formula. Okay, for any power that for any whole number power that you'd like to raise some binomial to, here's the way that you can find the terms in the expansion of that binomial. You'll recognize the notation here for combinations. You can do a combination of n items taken 0 at a time, or n choose 0, times a to the nth power, b to the 0 power, plus n choose 1, a to the n minus first power, b to the first power, and hopefully you'll see a pattern here with what I'm writing, plus n choose 2 times a to the n minus second power, b to the second power, and so forth, all the way until you get to n choose n times a to the 0 power, b to the nth power. Alright, as I said, there are several patterns here that we need to observe in order for this to be something that you would feel confident being able to use. Let me describe some of those to you. One of them is the pattern that's happening with these combinations that you see. Hopefully, you notice first of all that this number n corresponds with whatever power you're raising the binomial to. And then the bottom number in the combinations, or our value of r, begins at 0 and it increases by 1 each time until you get to where the top and bottom number match. Alright, so where the bottom number is equal to n. Secondly, I need you to notice that this bottom number corresponds every time with the power of the second term, the b from your binomial. Alright, I guess I probably should have mentioned one other thing first. I'll come back to that idea. Notice that after you do the combination thing here, the n choose 0, the n choose 1, you always have an a and a b, which come from whatever number is first in your binomial and whatever number is second in your binomial. And you start a as being to the nth power, and then you decrease that by 1 every time. So we go from a to the nth power to a to the n minus first power, a to the n minus second power, and so forth, all the way down until you get to a to the 0 power. And then whatever the second term in your binomial is, we're counting up, starting at b to the 0 power, then b to the first power, then b to the second power, and so on and so forth, okay? Now, again, this number right here matches with whatever the exponent for your second term is. You can see the zeros match up, the ones match up, the twos match up, and so forth. The n's match up as well. The last pattern I want to talk about right here before you've actually seen this put to use is that the exponents for the first and second term always add up to match whatever power you're trying to raise this binomial to. 0 plus n is equal to n, 1 plus n minus 1 equals n, 2 plus n minus 2 equals n plus 0 equals n. So that's a pattern that you ought to recognize. Now let me give you a very simple example with a binomial that you already know how to expand. Let's just say we want to square x minus 5. Alright, well, first of all, we need to know the value of n that we're working with, and that's going to be 2 because it's the exponent for our binomial. So we're going to have 2 choose 0 times, and then we're going to put an a, well, the first term here, which is x to the nth power, so x squared, and then we're going to take the second number, negative 5, and we're going to raise that to the 0 power. And this would be the first term in the expansion of the binomial. Alright, and then the second term we would increase this number from 0 to 1 right there. We'll do 2 choose 1. And we'll decrease the power of the first term. So we'll make that x to the first power. And we'll increase the power of the second term. So we'll now have negative 5 to the first power. All right, and then we're only going to have one more term in this expansion. So finally, we'll do 2 choose 2. And as soon as you get to the part where these two numbers are equal, you're at your last term, which will end up being the constant term, generally speaking. All right, and then we'll have x to the 0 power, because we're counting down until that was to the 0 power. And then we'll have negative 5 to the second power. All right, now for the purposes of this video, I'm trusting that you know how to calculate combinations on your calculator. There's that formula, n factorial over the product of r factorial and minus r factorial. But I'm going to trust that you know how to use your calculator for this particular video. All right? We can practice with the formula in class if you need to. 2 choose 0 is going to end up being 1. So we got 1 times x squared times 1, because that's what negative 5 to the 0 power is, plus, and 2 choose 1 is going to end up being 2. And we'll have x to the first power times negative 5, because that's what negative 5 to the first power is. And then 2 choose 2 is also 1. X to the 0 power is 1. And then you have negative 5 squared, so times 25. So then x squared minus 10x plus 25 is the expansion of that binomial. Now, you know how to square binomials already, so you probably already knew that this is what you got from squaring x minus 5. And so you see that the binomial theorem does work for expanding binomials. All right, well, let's try that for m plus 4 to the 5th power. See if you can pause the video and write out the expansion on your own to begin. And then unpause and see if you're doing it correctly. Now I've got a couple terms up there so far, and everything I'm doing fits the pattern that I showed you. I started, my n was the exponent there, so you see I have 5 choose 0. Always start that one as 0 and count up. Then these two add up to 5, the two exponents do. I've got the first term raised to the nth power, and I've got the second term of the binomial raised to the 0 power to begin. And I'm decreasing the powers of the first term while I'm increasing the powers of the second term. I'm going to go ahead and pause myself so that all the rest of this appears at one time on the screen. And now if you need to pause to just make sure that you've got all this correctly to begin, that's fine. And now I'm going to go ahead and start simplifying. Again, I'm assuming that you know how to do the combinations on your calculator whenever I go ahead and simplify. All right, so 5c0 is 1, and we got times m to the 5th times 1, so just m to the 5th. And I'm going to do a couple of these terms with it and just kind of write the rest. 5c1 is 5, and then you have m to the 4th times 4, so 5 times 4 is 20, m to the 4th. And then 5c2 is 10. We'll have 10 times 16, so 160. M to the 5th, or sorry, m cubed. Got to count down there. And so on. Not too bad, I hope, right? Okay, going to get you to try just one more expansion problem and then a couple of variations of questions that you can be asked to solve using the binomial theorem that you wouldn't want to solve, most likely, using Pascal's triangle. All right. We're going to do this expansion, and mostly I just wanted to throw in an example here, well, two things, where you've got 3x, a coefficient to go with your variable, and where the binomial is a difference instead of a sum, because you're going to notice a pattern whenever that happens. All right, go ahead and write out, using the binomial theorem, the pattern for each of the terms, and then we'll simplify them. Notice two things with the first term. In the expansion, that I took the first term to the binomial and I put it in parentheses and I'm raising that to the 4th power, so I'm going to get 81x to the fourth power instead of 3x to the fourth power, if you follow. And then I put the subtraction sign in with the second term, so I'm raising negative 1 to the 0 power. Then I'll do negative 1 to the first power, and so forth. So there's the rest of that. Again, pause if you need to take a look at all the terms, if you didn't already get that on your own. All right, and then the simplifying, we'll have 4c0 is 1 times 3x to the fourth, which is 81. Well, let's just do all this at once. This is going to be 81x to the fourth times 1. And then negative 1 to the 0 power is positive 1, right? So we'll just get 81x to the fourth right there. Here's where the negative sign is going to start having an effect. You notice we have negative 1 to the 0 power, which is an even number. Then we have negative 1 to the first power, which is odd. A negative number to the second power, which is even. The signs of my terms in my expansion are going to start alternating because I'm raising a negative number to an odd power, followed by a negative number to an even power, then a negative number to an odd power, and so forth. So we're going to get the first term as positive, then negative, then positive, and so forth. All right, so 4c1 is 4. I'm going to have 4 times negative 1, which is negative 4, times 3, so negative 12. Oh, no, negative 12, right? Because we have to cube that 3. That's 27x cubed. 27 times 4 is 108. Times negative 1 is negative 108. All right, here we have 3x, the product of 3 and x squared, so you get 9x squared. 4c2 is 6. So 9 times 6 is 54. 54 times positive 1 is 54, so we get plus 54x squared. All right, and so forth. You can go ahead and fill in the last two terms on your own. And that's expanding binomials with the binomial theorem. All right, now an advantage to the binomial theorem for an expansion as opposed to the Pascal's triangle is that you can look at it, well, one of the advantages is that you can look at expansions that have some pretty big exponents here, like 7, and you're going to be able to work with those without having to know 7 rows of Pascal's triangle. But another advantage is that you can find specific terms. What we're going to do in this example is we're going to find the c cubed d to the fourth term in the expansion of 2c plus d to the 7th power. All right, so we're looking for a very specific term. Now, think about where the c cubed d to the fourth term would come into play. Remember that in an expansion, that the first term and the second term, their powers always have to add up to the power of whatever you're trying to expand to, and you see the 3 and the 4 add up to 7. Do you know which term this is? It's going to turn out to be the 5th term, all right? But here's really what's more relevant. To find that specific term, we need to know what the value of n and r will be for that term, okay? And we find out the value of n always by looking at what power we're raising the binomial to. And remember that this value r down here always corresponds with the exponent for the second term, and the second term being the d. So that's going to be a 4. Okay? Then we'll have times 2c to some power that I'll discuss in a moment, and then times d to some power. Now again, this number always matches up with this exponent right here, and they always add up to 7. Or not necessarily 7, but they have to add up to be the value of n anyway, which is 7. Okay, so this would be the c cubed d to the fourth term. And if you don't see that quite yet, you'll see that it does give us that whenever we actually do the math. The 7c4 is 35, and then we'll have times 8c cubed d to the fourth, and then 35 times 8 equals 280 c cubed d to the fourth. All right, so there's the value of the c cubed d to the fourth term in that expansion. Got one more example that I want to show you in this video that involves a binomial theorem. It's kind of that last one backwards in a sense. It's telling us that the coefficient for the x squared term in the expansion of x plus p to the 6th power is 3,840. And it wants us to find the value of p that would make that true. All right, so in other words, p is going to be some number like 7, for instance. All right, and we got to figure out, well, for the x squared term, what value of p would give us 3,840 x squared. Now we're going to use the same basic idea that we did in the last example, where we know the value of n for the term that we're using, and we kind of know the value of r as well because we're looking for the x squared term. But you got to be careful with that one. Let me see if I can show you what's going to work out here. We're going to get 7, choose 5. And I'll see if I can tell, oh, not 7, but 6, right? We want a 6 right there. 6, and then choose 4, actually. All right, times x squared times p to the 4th power. Now, how did I know that this was going to be a 4 right here? Well, I knew I was looking for the x squared term, and so that would be the exponent that goes along with the first term from the binomial, and I knew that these two had to add up to 4, so I put a 4 right there, and, of course, I knew these two numbers had to match up with one another. Okay. Now, in this problem, we're saying that we know that the coefficient for this term is 3,840, and since it's the x squared term, we know this term is supposed to equal to 3,840 x squared. And so now all we've got to do is solve this equation for p, and it won't be nearly as difficult as you might think that it is. For 1, we've got an x squared on both sides of the equation that we can divide out quite easily. So those will cancel, that'll cancel. And then 6 choose 4, we can do that on the calculator. And that gives us 15. So 15p to the 4th equals 3,840. All right, and so 2 more steps here. We're going to divide both sides by 15, which will give you 256. P to the 4th equals 256. And then you got to find the 4th root of 256, or raise both sides to the 1/4 power if you prefer to do that. And it turns out that it's 4 to the 4th power that gives you 256. We don't need to worry about the negative value, although, well, to tell you the truth, they would both work, wouldn't they? All right, so let's put plus or minus 4 then for our answer. Because even if we had x minus 4 to the 6th power, we would have negative 4 to the 4th power, which would give us positive 256 still. They would still both work. All right, so there's how you use binomial theorem to expand binomials and how you use it to work with specific terms in the expansion of a binomial. Thanks for watching. Hope this has helped. I will see you next time.